So today we're going to be working on numbers on the complex plane. And so what the complex plane is it involves an area called lateral numbers. What we are used to up until this point is numbers that either go in one direction or in the other. We have what we call the positive and the negative axis. You either have more of something or less of something. What we're introducing when we say the complex plane, we're now saying, hey, we can have something else. And what this means is that, let's say you have 2 apples, and I have 2 oranges. If I have 2 and you have 2, we both have 2, but you don't have more fruit than me. You have a different type of something. I can take your apples away, but that doesn't necessarily add to my value. We're looking at, and that may not be the best analogy, but the idea is we're comparing something new, something that's still 2 units away. You're still 2 units away from being hungry, but we're not in the same direction. You have an apple, I have an orange. So we're introducing a second dimension to the number line. And this is what we call lateral numbers. Now, the fun part is a lot of students ask, well, why does I represent a lateral number? Why wouldn't L represent a lateral number? They almost look the same. Why use an I? Well, that comes from way back when mathematicians called René Descartes, when they were first looking for what is the square root of a negative number. They were looking at quadratics and how they work out, and he said, hey, these things are impossible. You might as well call them imaginary. Along several other things, and several other mathematicians said, I cannot find a use for this thing. Why don't we just say this is stupid? It's imaginary. It's impossible. You can do this math, but it doesn't mean anything in the real world. So they started denotating it as I for those impossible imaginary numbers. A couple centuries later, we come around, we find that in fact these lateral numbers have many different uses, especially when we go down to quantum mechanics in the quantum realm. A lot of different forces use things that represent lateral numbers. A lot of computer programming use them as well. So albeit in his time, René Descartes said these are impossible, I will never find a use for them. We have in fact found that this is a highly useful skill, especially as computer software is developing. So it's worth figuring out how do numbers work in the lateral plane. So let's take a look. Whole idea is I is the square root of -1. So if I have I squared, I will get -1. That's the idea. So whenever we break down any sort of square root, typically we would break it down into 2 different square roots. I'd say, okay, a -49, I'm going to break this down into the square root of -1 and the square root of 49, both of which I can find values for. The square root of -1 is going to give me I, because what number times itself gives me -1? I. When I say what number times itself gives me 49, I get 7. So my final answer is 7I. Boom. Likewise, if we don't want to break it down into just 2, let's say 98. 98 isn't a perfect square, so we're going to have something left over. So first off, let's break down 98 into the square root of -1 and the square root of 98. Now 98 I can divide by 2, so I'm looking at the square root of 2 and the square root of 49, of which I know the square root of -1 is I know the square root of 49 is 7, but unfortunately I can't reduce down my square root of 2. So in this case I have a 7 and an I with a leftover square root of 2. Now, the same thing works for these numbers as do variables. If I have variables in here, most of the way that we're going to break these down is by factor trees. Now, I'm not going to write out the square root each time. Typically, the way that we write these out is we would write them out as a -1, a 16, and then the older fashion for these variables is I would write out an x and an x. What I would do right here is I would say 4 and 4. and I would circle pairs of numbers. Okay, the square root of 16 is 4 by 4. I have a pair of 4s, which means a 4 can be rooted out. I have a pair of x's, which means an x can be rooted out. Likewise, I know that -1 can be broken down into I and I, which means additionally an I can be rooted out. So I have an I, a 4, and an x. These being accepted constants, I'm going to say 4i followed by my variable. Perfect. That's an alternative way to write it. This is to utilize the root symbol each time. This is to go for bases and say, I'm not caring what the square root of 49 is. I want to find bases. And this will help you if perchance you don't spot the roots immediately. So let's say with this one, I don't spot the roots immediately. I say I have a -1 and a 300. I say I have a 3 and a 100. I don't recognize that this is a perfect square. Let's say I continue to break it down into a 2 and a 50, a 2 and a 25, and I say, hey, I recognize that the 25 is a 5 and a 5. Well, what I can do is I can say, hey, I'm going to pull out a 2 and pull out a 5. Likewise, my I and my I, I'm going to pull out an I as well. And with my W's, 1, 2, 3, I'm going to pull out 2 W's. Now, unfortunately, I didn't pull everything out. I still have this 3 left behind, and I have this other W left behind. And what this means is that my 2, my 5, my I, and my W all come out. My 3 and my W get left behind. Then I simplify what I can. 10iw square root 3w. This is what we call the split factors. Boop, boop. 2 and 2, because they're at 2 different spots on the tree, they'll root together to make a square root of 2. I could have alternatively done this question. Let's say I take the square root of -300, w cubed, and I do it like we did in number 3. And I say, okay, that's the square root of -1 times the square root of 300. That's the square root of 3 times the square root of 100. This is going to be the square root of w squared and the square root of w. I know that I can break down 3 of these roots. That's going to give me an I, that's going to give me a 10, that's going to give me a w. I have to leave behind the 3 and the w. In this case, I have a 10iw square root 3w. Either way that you do this, with the split factors, where you circle pairs of numbers, or if you just recognize where your perfect squares are, you can do either way. So what I want you to do is I want you to try out number 9 and number 11. I want you to pause the video, give them a shot, resume it when you're done, and see how you did. Okay, let's see how we did. So the first way I'm going to show using the traditional method. I'm going to say right here I have the square root of -1 and the square root of 25. Right here I have the square root of x squared because squared and squared will make x to the 4th, and the square root of y squared. All of which, 1, 2, 3, 4, and 5, I can root. Square root of -1 is I. Square root of 25 is 5. Square root of x squared is x, x, and y. If I reorganize that, I have a 5ix squared y. Perfect. The second one, because I don't know the square root of 160, I'm going to break this down according to the split factor tree. I get a -1 and a 160. I get a 2 and an 80. I get a 2 and a 40, 2 and a 20, 2 and a 10, 2 and a 5. I have 1, 2, 3, 4, 5, 1. Okay? So I have 1, 2. It's going to come out. 1, 2 that's going to come out. Oh, and I know right here, I know an I is going to come out. I left behind a 2, a 5, an N, and a Z. So if I rewrite that, I have I times 2 times 2 times N. Left in the square root, I have 2 times 5 times N times Z, which is going to simplify to 4in squared, square root of 10nz. And there we go.